In previous part, we talked about linear mapping, basis change, etc. Now in this part, we are going to talk about the fundamental theorem of linear algebra. But before that, let us coin some terminologies. The first one is kernel. Kernel is the set of elements of the domain. So let me tell you, when I have or when we have a mapping phi v to w, v I am saying it's an input space and w I am saying that it's an output space. Now kernel is a linear kernel of a linear mapping is a subset of the domain, that is the input space, which maps the points which are mapped to the zero vector. So it's an elements these are the elements of the input space that are mapped to the additive identity of the output space, and that is called the kernel. The trivial solutions is, if you have if you have only trivial solution, if you have only trivial solution to this equation, only trivial solution, then it means the cardinality of the kernel is 1, because only 0 is actually mapping to 0. But if you have non-trivial solution as well to the equation Ax is equals to 0, then definitely there are many points that are actually mapped to 0. And in that case, we have kernel even other than zeros. And let us move towards another term called image of linear mapping. Now, image of linear mapping is the set of all the points in the codomain or in the output space that are associated with some or other element in the input space V. So it is the set, which you can say like, yes, all the elements are mapped to some or other thing. So all those w's which has been associated to some v in vector space V, the input space. Okay, now interestingly, when I say uh, okay, image is different from w. So it is different from w, you can see it is different from w. Why? Because it is quite possible that you have more elements which are not yet mapped, not mapped from any element of input space. So in that case, you might have uh, you might be having mapping something like this, wherein this this portion, this purple portion, is not mapped to any of the element of V. This is this is not required, and this shaded region, this this green shaded region, I'll take the green shaded region again. So this green shaded region is the image, because that is the whole thing V is mapped to. And if I take this red thing, this particular portion, every element of this portion is mapped to 0 of vector space V, and that is called kernel of phi. This kernel of phi, right? So that is the terminology. Now, uh, now image of 5 will definitely have the origin. Image of 5 will definitely have the origin. Okay. Now there is another thing. There is a theorem which says that for any linear mapping phi, the origin of the input space will always map to the origin of the output space, which and the proof you can see here. So this proof is simple, which I think you will be able to do, because it says that if it is an additive identity, it should follow this thing. And if I take the linear mapping both the sides, this should follow. And since it is a linear mapping, therefore you can write this as this expression. And now since these are the two things in the equality, you can take one particular, means you can take the additive inverse of this particular thing, both the sides, additive inverse of this particular thing both the sides, and you will get something like this and this. And since you are adding the additive identity to this, additive inverse of this, so you get an additive identity of the output space here, and additive identity of the output space here. Now additive identity is when added to any vector of the output space will give the same vector. So which essentially means that the zero or the additive identity of the input space is mapped to the additive identity of the output space, and that's the proof. Now definitely you will agree that for any mapping phi v to w, image of phi will be a subset of w, and similarly kernel is a subset of vector space v, the input space. So both of them are subspaces. This is a subspace of w and this is a subspace of v. So definitely both of them must have their dimensions also. Now image of phi is is directly dependent on the linearly independent columns of A, which I mean to say this way. Let us suppose that this is the transformation matrix corresponding to the linear mapping, right? And your linear mapping goes from Rn to Rm, right? Now the input space the input space is from Rn, right? So the x is belonging to Rn and Ax is belonging to Rm, right? Now notice that the image of phi is nothing but all the items that can be written as Ax or that can be obtained from Ax, and where x is in Rn, right? So this is your domain, this is your domain, the Rn is your domain, and Ax gives you the images. So all the images, set of all the images you have taken, and that is this. Now this Ax can be expressed as a linear combination of columns of A. Now these linear combination of columns of A, so it's like a span of column vectors of A. It's like a span of column vectors of A. So definitely the dimension of image is equal to the dimension of column space of A, which is nothing but number of linearly independent vectors of A, which is actually the rank of A, right? So that's the one core thing. and and we know, if you are talking about the kernel of our kernel of this uh, mapping, then we are referring to the free variables, because the free variables are corresponding, or the free variables are responsible to make the non-trivial solutions to ax is equals to 0, right? So the non-trivial solution of ax is equals to 0 are coming from the kernel, are coming from the free variables. So the dimension of the kernel, which is the set of elements, kernel is the set of elements that are mapped to 0. So, so map to 0 means x is equals to 0. For those x for which ax comes out to be 0, this is the set of x's. Kernel is the set of such x. So, so we can say that the dimension of kernel, which is nothing but the number of free variables, the dimension of phi, which is nothing but the linearly independent columns of A, which is equal to rank, is equals to the dimension of V. V is the dimension of V is the number of columns of A, or the elements in each row of A, elements in each row of A. And this is called the fundamental theorem of linear mappings, which connects the kernel space dimension and the dimension of mapped space and the dimension of the input space. So that's the beauty. So in the next lecture, we are going to talk about affine spaces. Till then, thank you. The rest of the things can be covered easily, so that I have a little bit left for you to see from the notes, right? So we can notice that image of phi, if the dimension is equals to dimension of w, which means essentially means that image of phi and image of and w are same, and that becomes the non-2 function. If the dimension of image of phi and the dimension of v is same, it's a one-to-one, because both the dimensions are same. The input space dimension and the output space dimension is same, and hence both of them are equal, and it is one to one. So that makes a bijective function, uh, which means you are moving from Rn to Rn, right? That's it. That is for now, and in the next part we are going to talk about affine spaces, the spaces that are a little bit shifted away from the origin. Thank you.